All right, guys. So we are starting Unit 13 or Chapter 13 today, which is Unit 6 for us. In this unit, we're going to continue looking at some of the kind of cool stuff of geometry, where it shows up in nature and things like that. We're going to look at it in the context of Chapter 13, talking about what are called the Fibonacci numbers and the golden ratio. So starting with in section 13.1, the Fibonacci numbers. And in fact, we just did that intro activity where you got to see some of the cool stuff that already happens with the Fibonacci numbers. Now we're going to get a little bit more into the math part of kind of how they work. So to begin with, the Fibonacci sequence, as we saw, is this sequence right here. You've got 1, 1, 2, 3, 5, 8, and so on. It is what's known as the Fibonacci sequence. The individual numbers that are in the sequence are what are known as the Fibonacci numbers. And we talked about in class and during the activity that to get from one number to the next, you simply add the two previous numbers. In other words, 1 plus 1 gives you 2, 1 plus 2 gives you 3, 2 plus 3 gives you 5, and so on. Now, in the textbook, they give you an example of what is called Fibonacci's rabbit problem. I would encourage you to read that if you get a chance. It's at the very beginning of the chapter. We're not going to talk too much about it here. What I did want to mention, though, from this slide is that the Fibonacci sequence is infinite. It does continue forever. And what's kind of interesting is, except for the very first two ones that you have, each sequence is going to be the sum of the two numbers before it. In fact, some people will actually start it with a 0 followed by a 1 to look something kind of like this instead. And that would still kind of follow that rule, and so we'll kind of go back and forth on kind of where it starts. But really, other than those two ones, there's not even another pair of numbers that repeat, which is kind of interesting. So the way we talk about each separate Fibonacci number is with this notation. We use a capital letter F for Fibonacci, and then a subscript that indicates the position of the number in the sequence. And so if you remember, let's just write out the sequence. So 1, 1, 2, 3, 5, 8, and so on. We won't go past that. But what we'll do is we'll use capital F sub 1. So you say SUB for subscript. F sub 1 represents this first number 1, whereas F sub 2 represents the second one. Then F sub 3 would represent 2, F sub 4 would represent 3, and so on and so forth. In other words, what we can do is we can assign each of the numbers in the Fibonacci sequence a notation that's really easy to use. In fact, it even tells you that the 10th number in the Fibonacci sequence is 55. So if you were to continue this out to 55, that would be the 10th number in the sequence. In fact, if you wanted to, we could at least talk about f of 100. That would be, if you continue to do this for quite a bit longer, eventually you get out to f sub 100. Now, we don't know what number that is quite yet, but we're about to find a formula which is going to be very useful at helping us find that number. So, on this slide, it just talks to us a little bit more about those Fibonacci numbers. Obviously, Fibonacci number two places before f sub n, we could write as f sub n minus 2, so you can kind of use this subscript, and that's going to be what's useful in this recursive rule. So remember, a recursive rule is just one that defines a sequence in the numbers. It basically sets up the rule that generates the Fibonacci sequence. In other words, you just continue to add the two numbers that are at the end of the sequence to get the next number, and so on. In other words, a way to say that is that each number of the Fibonacci sequence is the sum of the number that came right before it. So this is right before f sub n, and the number that came to before it. So that would be f sub n minus 2. Again, probably makes a little bit more sense when you just think about it in general. When you try to use this recursive rule, you can still use it, but it might get a little bit confusing. Now what we can do is we can go ahead and calculate very large numbers using that recursive rule. To do so, we first have to define the first two numbers. We have to say that f sub 1 is 1 and f sub 2 is 1. Those are the only two that get special values. They're what are called anchors for our recursive rule. In other words, they're the seeds, if you remember when we talked about seeds for the Mandelbrot set in chapter 12, but they are the seeds of our Fibonacci sequence. They're the only two where this rule, this formula, doesn't really apply. You have to have these two values before you can find everything else. Now, once you've got those, you can really find any number you want. So if you wanted to find f of 100, if you had some patience and a calculator, you could just keep on cranking out those numbers until you got up there. In fact, just to show you how big those numbers get, eventually you'd get to f of 97, f sub 97, which is this number right here. And I won't even try to say it out loud, but you can see that it's a number well into the trillions, quadrillions, even up into those very large numbers. And if you keep going, you'd get to f of 98, which is, again, an even larger number, f of 99, which is a very large number. And finally, when you take this number right here, plus this number right here, f of 98 plus f of 99, it's going to eventually add to be this number right here. So f of 100, we finally have it right here for us to look at. We didn't necessarily find it by doing it ourselves, but it would take quite a bit of time, so it's kind of nice that they were able to find it for us. Now, just to give you an idea of how big that number is, if you were to convert that to dollars, here's what that dollar amount would be. And if you think about how much money that's worth, even if you took out $100 billion for yourself, which, hey, $100 billion, plenty, right? That's more than enough that you could possibly have. And then divide everything else that's left over by every other person on Earth, which at the time these PowerPoint slides were made back in 2014, that population was about 6.7 billion. So a little bit more people in the world right now. But at 6.7 billion people, each person that's left would still have $500 million for themselves. So think about how much money that is. If everybody had that much money, that's a very, very large number that we're dealing with. So obviously you can see that while that number, you can find it the way we talked about, just continuing to add numbers one after the other, it would take a lot of time. And so it'd be really nice if there was another way to do that. In fact, Leonard Euler actually discovered a formula for that. If you remember Euler, we talked about him back starting in chapter 5, actually. Our very first unit, we talked about Euler and Euler's algorithm for all that kind of stuff, or Euler's paths and circuits. But he actually discovered a formula in 1736 where you didn't have to have the previous Fibonacci numbers. Unfortunately, that formula was lost. But the good news for us, it was rediscovered 100 years later by a French mathematician by the name of Jacques Binet. And somehow he ends up getting all the credit, even though Euler discovered it first. And so we call it Binet's formula rather than Euler's formula for that reason. So here's what Binet's formula says, is that any of the Fibonacci numbers, f sub n, can be calculated by taking 1 over the square root of 5, multiplied by, inside of those brackets, 1 plus the square root of 5 over 2 to the power of that Fibonacci number n that you would want, minus 1 minus 5, or square root of 5 over 2 to the power of n. In fact, there's an even more simple formula for it, which I'll go ahead and write for us right now, which is that you can actually just take 1 plus the square root of 5 over 2 to the power of n and divide that by the square root of 5. So an even more simple formula is this right here. In fact, that's going to be the formula that we will use in order to find some of those Fibonacci numbers that we've been talking about. So let's go ahead and use that right now. So again, we'll look at it for f sub 100. So in order to do that, you're going to need a calculator that can handle some very, very big numbers. And in order to make that easy for you, I've gone ahead and included that as part of our class on Canvas. So if on Canvas you go to our modules, it looks like it went to mobile version. Let me go ahead and get this expanded here. Here we go. So if you go into the modules for our chapter 13, and click on Calculator for Big Numbers, it's going to have this calculator right here for you, which we can actually use to help us find some of these very large numbers that we're going to need to talk about. So let's go ahead and do that now. In fact, I'm going to go ahead and expand this a little bit, and we'll go ahead and use it in just a moment. So let's say we wanted to use Binet's formula to find f of 100, or f sub 100. Then what we're going to do using Binet's formula is we would say that f sub 100 is equal to 1 plus the square root of 5 over 2 to the power of 100. All of that divided by the square root of 5. And so if we want to type that in, what we'll do, and we'll do it probably in a couple of steps. Let's just start by taking 1 plus the square root of 5. So if we take 1 plus the square root of 5, which it'll write it kind of weird in the calculator, up above you should be able to see that number like you normally would. So that tells us 1 plus the square root of 5 is about 3.2. We'll then take that and divide by 2. That'll give us this number right here, 1.618, and so on. More on that number later on. In fact, that's going to be a very important number when we look at the golden ratio. In fact, for those that did part 2 of the activity, that number should look very familiar to you. We're now going to take that number and raise to the power of 100. And we're going to get a very, very, very large number. Here's where this calculator is very important, because without this calculator, just a regular graphing calculator is not going to be able to handle a number that big. Very last step. So we've taken 1 plus the square root of 5. We've divided by 2. We've raised it to the power of 100. We just need to now divide by the square root of 5, and that should be it. So divide by the square root of 5 is equal to, and we get this number right here. 354 is how it starts, 224, 848, and so on. And then when we round this to the nearest whole number, which again would be a little bit off from this. I think the calculator was off just a little bit there. But when we round to the nearest whole number, it's going to give us a number very close to that one that we were just talking about. Now, why are Fibonacci numbers so special? Why do we talk about them? Well, it turns out that they are all over the place. Just some simple examples from nature. You've got lilies, irises that have 3 petals, buttercups, columbines have 5, cosmos, rue and anemones have 8 petals, and so on. And it's really kind of interesting, these different flowers that actually increase in the number of petals based on the Fibonacci sequence. Another example is actually found in pine cones. So it's actually the case that as you go up through the different sections of the pine cone, that you actually can see Fibonacci numbers in the spirals there. Just some other examples. We talked about pine cones and flowers. Artichokes are another example, and pineapples, actually, interestingly or not, are also another example of that. You can see also sunflowers, lots of different things. I would encourage you to kind of, on your own, look up where Fibonacci numbers show up in nature. Really kind of an interesting thing to look at when you see those numbers in the real world. Alright guys, so that is it for right now on the Fibonacci numbers. And the next section we'll talk a little bit more about what's called the golden ratio. Until then, have a good rest of your day.